Thank you, Mike. And I would like to first thank Francois, who indeed did almost all of the work in organizing this event. And I have a long list of things to thank René for, but I will postpone that. Instead, I want to say that René's birthday is not anytime soon, but we like to think of these conferences as birthday conferences. And so I would like to congratulate René with his birthday in French, but I don't speak French, so I outsourced it to my daughter. So let me play a short video, which is the main part of my presentation, really.
Joyeux anniversaire, René.
And now we can continue with the less important part. That is my work on really work on Stefan problem, which turned into mean curvature flow, and which, to our surprise, became connected to mean field games. And so let me tell you all about that. So I will start with a very old problem that has been solved and has been around for a very long time. This is mean curvature flow. It's a flow described by this simple equation here. But behind this equation, there is quite a bit going on, right? So this is more like a symbol, right? How they do it in differential geometry, right? One line, but behind it, there is a whole theory. So really, imagine a moving domain, gamma, that is a function of time, and we look at the interface, so the boundary of this domain, and for simplicity, think of this as being a smooth, nice curve, such that I can define the orthogonal direction at every point, and V will denote the velocity in this orthogonal direction. It may expand, it may shrink, and H will be the mean curvature, so the average of the curvatures in each direction, at each point of the boundary. And so mean curvature flow says the following, that the velocity is negative of the curvature. Of course, the negative comes from the assumption on the signs. So I think of H being positive if the domain is convex there, and V being positive means that the domain expands, right? With this sign convention, you get this very simple equation. You can put a constant here, but it doesn't matter. It scales out once you change your time by scale. So what is nice about this evolution is that, intuitively speaking, even though, again, it's a lot, right? So I start with some domain, and I have to make sure that it stays smooth so that everything is well defined. So in what sense I'm actually thinking of this solution is not clear, right? But intuitively, what's happening here, you can prove it rigorously, is that if I do have a solution like this, then it will be regularized. And this evolution is regularizing in the sense that the length of this curve, so let's say in dimension 2, you really have a curve, right? That will be decreasing over time, right? That's the regularization phenomenon. And so this is just how you can visualize this. In the convex parts, what will happen is the velocity will push, the motion will push inside the domain, which means it will decrease the perimeter locally, right? So think of the convex part. If you move outside, you increase the perimeter locally, but if you move inside, you locally decrease it. So this is what happens here. So here you push outside, here you push inside. And there's a very nice video, again, one more video, that is on the website of Sigurd Angenent from University of Wisconsin, which I love to show as really the best illustration of how mean curvature flow goes. You can start with a very ugly thing, but ultimately it becomes this, and it will ultimately shrink to a point. And in dimension 2, this is really what happens. So you can prove that this is all that can happen. If you start with the connected domain, simply connect the domain, this is all that can happen. All right, so I don't know if we should wait. Yeah, it's going to disappear very soon. But basically, you see this regularization phenomenon. All right, so going back, because afterwards, it starts showing YouTube videos that this may be embarrassing. So, all right, so how do we make all of this rigorous? So one way is really to design a PDE out of it. And this is done through the so-called level set function method. Without loss of generality, you can assume that your domain is given by a sub-level set of some function w of t and x, right? And then it turns out you can express now your velocity and your curvature through this function w. It's a very simple way. Plug it back into your equation, you get this. And this is actually a nice parabolic PDE. So you start with something that is kind of differential geometry object, which is hard to define precisely, but you end up with this. And in fact, now you don't even care that you have a smooth domain, right? You don't need all this smoothness. You can just think in terms of W function. And this is still not a trivial equation, but it satisfies the comparison principle. So essentially, the end point of this theory was, well, at least the well-posedness part, was these two results, who independently prove the existence and uniqueness of a viscosity solution to this equation using comparison principle. Okay, so that's sort of the end of that. But of course, not the end of my presentation. What do I want to do? What will I talk about? I will talk about an extension of that equation, which I call a second order mean curvature flow. Now, I skip a lot of motivation how we arrived at this particular formulation here, but let me just say that it's not out of the blue. It comes from a Stefan problem, from our analysis of Stefan problem. It is also connected to other physical phenomena. For example, the oscillation of a soap bubble is described by a similar equation with a slightly different right-hand side so that it becomes periodic. And no rigorous results exist, actually. Only numerical computations are available for this equation. Okay, so what is this? Again, we have a moving domain gamma. We have the same notation, h and v, for the mean curvature and velocity. And now we have a constant. Things will not scale. Constants will not scale out now. So I need to have this constant gamma. This gamma has a physical meaning. It's a surface tension coefficient. So again, for those who are interested, if you're not interested, just ignore it's a constant, some constant, right? And so instead of prescribing velocity now, I prescribe the acceleration, so v dot. V dot now is proportional to h times v and has this quadratic term as well there. Okay, it looks a little bit, strange. Yeah, indeed, it's a little arbitrary here. Why? Well, again, because it comes from Stefan problem, that's why. But let's just take it as given, and let's just assume that this is an interesting object to study, right? Now, what can I say by just looking at this equation immediately is the presence of this v here essentially makes sure that v itself will not change its sign. So as it becomes smaller, its derivative will also decrease. So if you have, for example, a domain that initially is expanding at every point, it will continue expanding. So that's a nice feature, right? Yeah. No. So v is a scalar. It's a scalar. So this is the length of the velocity in orthogonal direction. That's how you think. With a negative sign, meaning that you look at minus the orthogonal.
But everything is in dimension 2.
Well, I will switch to dimension 2 at some point, but so far it's arbitrary dimension. Yeah. So this is surface. Yeah. So again, so we look at the velocity in the orthogonal direction always, right? And with a negative sign, meaning that we're pointing inside the domain. Yeah. Okay. So again, so it's not a regularizing flow because you don't have that feature of decreasing perimeter anymore. I'll show you on the next slide why. Visualize that. But it does have one good feature that mean curvature flow did not, is that you have this monotonicity, right? If you start with expanding set, it will keep expanding. So you will not have this weird kind of motion, expanding and contracting. Now, why is it not regularizing? Well, there's a simple picture. You see, now it's only the acceleration that points in the direction of decreasing perimeter. So think of it like this. If you have, for example, velocity here that's already pointing outside at the convex part, it's increasing the perimeter locally. So your acceleration from the equation will help you, but it will not help you immediately, right? It will not kill the velocity immediately. So you'll still be expanding for a little bit, increasing the perimeter before you start moving in the opposite direction, right? So it's regularizing to some extent, but not exactly. It's almost like one intuition I have for this is think of a gradient descent where instead of choosing the velocity with which you move, you only choose the acceleration, right? So you're trying to push yourself in the direction of decreasing a function, but you cannot really do it immediately, right? So you may have really strange phenomena in that case. So that's the challenge of this problem. That's the challenge. But let's try to mimic what was done for the mean curvature flow. For the mean curvature flow, the solution was obtained by looking at the level set function. And here we do something similar, but because of this monotonicity, we have the luxury of choosing this level set function so it doesn't depend on time. In other words, my level set function will be just w of x minus t. I only can do it because I have, let's say, always expanding domain gamma. And it turns out that if this w has another meaning, so you can define it as the arrival time function. So it's the first time that your domain reaches point x. So here we're thinking of expanding domain all the time. All right? And very similar formulas hold, and you can plug them back into this equation. It's a little more work, but you arrive at this PDE. So again, you get a PDE for the something like level set function. Now we call it arrival time function. And we call it, by the way, cascade equation. I again, have to skip that part, why cascade, but it goes back to the work of Francois, Etienne, and their co-authors, actually, on the cascades and integrated fire models. But we, of course, have gone a very long way from that equation, but in fact, it's very much connected. Again, and separately, I will be happy to explain in what sense. So we call it cascade equation. This cascade equation is hyperbolic. That's the problem. It doesn't have a comparison principle. And that's the main challenge, really. It also has the boundary data, which is W 0 at 0, so your points at the boundary are reached immediately. And the initial gradient is 1 over the velocity, initial velocity. So you solve this equation with the prescribed initial velocity at the initial boundary. Okay. All right, so what are the challenges? Again, let me summarize. So what are the bad news? So first of all, classical solutions are out of question. That's clear even for the mean curvature flow, right? Because you divide by gradient, and you know you will have local maxima for this W, at which point this is just not well defined. But there are other issues. Comparison principle does not hold. That's a really bad news compared to mean curvature flow because it's a hyperbolic equation. And you don't see it's hyperbolic, but once you expand the terms, just trust me, it is. Almost every time I present this, somebody doubts that. So, but I'm always too lazy to put the exact expansion because it just takes too long to expand this and see all the quadratic terms. But it is hyperbolic. But what is even worse is that simple examples show you that. So you cannot look at viscosity solutions because of lack of comparison principle. You cannot look at classical solutions. Okay, let's try to look at weak solutions, right? Integrate with a test function. It turns out that when you do this, this equation does not actually hold. It only holds with inequality. By the way, the same is true even for mean curvature flow. If you look at that PDE in a weak sense, it actually is not satisfied. Okay, and again, there are physical reasons why. So let me try to convince you of that in a simple example where my initial domain, so we go back to one dimension, right? So trivial case, there's no curvature, curvature H is 0. And we start, so this is the boundary, so your initial domain is the complement of 0, 1. And your gamma is expanding, but that means this interval is actually shrinking, right? Of initial symmetric velocities at 0 and 1. So these points are just moving towards each other. Now, it's clear what the solution looks like, right? I mean, you have no acceleration. You have constant velocity, 2 points moving towards each other. I mean, W must look like this, right? It's clear. But when you look at the cascade PDE, it becomes this. And when you plug the correct solution into it, you get non-trivial right-hand side. It's this delta function that you accumulate exactly in the midpoint. And physically, what happens here is that you can think, again, I'm not sort of pretending that has physical meaning, but you can think of the quantity gamma plus 1 over gradient of normal with the gradient of W as energy. And when the 2 points meet, it's like there is no boundary anymore, right? So the boundary energy that used to be concentrated at the boundary, moving boundary of your domain, it simply disappears because boundary itself disappears. But that's a violation of the energy preservation, right? And so for the same reason, in fact, the PDE for the mean curvature flow also is not satisfied in a weak sense because energy is not preserved. Once that point in that picture, in that video I showed you, once that thing shrinks to 0, shrinks to nothing, then the energy disappears. So you really cannot think of this as an equation, but rather inequality in a weak sense. And so now, okay, now that we know all the challenges, what do we need to do? What is the outline of the rest of my talk? So first of all, we have to accept the fact that we're not solving it with 0 right-hand side, but we have to put some negative measure there, minus d mu. Okay, now here's the approach. So it's actually very similar to many things that happen in stochastic control. Very often you think of a solution really as a smallest super solution, right? And that has a meaning. So I'm going to call solutions to to this equation, super solutions. They're not really viscosity super solutions. We don't have comparison principle, but I'll just call them for simplicity super solutions. And the idea will be to first choose a notion, because even with this relaxation, right, I still don't know how to define a solution yet, right? I don't know, but I will choose a definition. Then I will define the solution to my original equation as a minimal element in certain sense that has to have meaning, physical meaning, of this space of supersolutions. Okay? And then to obtain existence of this minimal element, I will just need to prove compactness of my space of supersolutions. So that's basically the rest of my talk. Okay? And of course, any questions are welcome at any time. Please feel free. All right, so let's start with part 1. How do we define a notion of a solution? This is where we stumbled across the connection to mean-field games. It was never a plan, sorry Renee, but I never plan to work on really mean field games in the classical PDE notion. I've worked on, say, corner cases, special cases, but never on the classical PDE version of mean field games. But we had to, like, it just came up. So what we're going to do here is the following. It turns out that just like Feynman-Katz formula often gives you a probabilistic representation of a solution, let's say, to elliptic or parabolic equations, in the same way here, the value function of a mean field game becomes a, I call it a particle representation, or like Feynman-Katz representation of a solution to this PDE. And I will make this precise on the next slide, but for now, let me give you intuition why this happens, okay? So, and this happens, in fact, for a very simple reason. This is our equation we're trying to solve. I'm back to 0 right-hand side because this is heuristic, right? So here also I introduced a normalizing constant. This constant is just meant to turn positive measures into probability measures, okay? But it also introduces new notation, which is the Hausdorff measure, and this measure theoretic boundary. So in the remainder of my talk, we will use methods from geometric measure theory. And so in that theory, there is a notion of a measure theoretic boundary. Roughly speaking, it's a boundary. Every point is on this measure theoretic boundary if for any small ball, you have a non-zero fraction of points inside the domain and outside the domain in that ball, okay? And so this is a Hausdorff measure of dimension d-1, and so this kappa is essentially the integral, the initial energy, the initial boundary energy you have. This boundary energy is made of two parts, velocity and gamma, which stands for surface tension. It's like just being on the boundary costs you something, costs some energy, and that's the effect of surface tension. Okay, so if we introduce this change of variables, so purely symbolic, again, just introduce this quantity called Q, plug it back into this equation, I get a Fokker-Planck equation, trivial stationary version of Fokker-Planck equation. Translation along this vector field, but it's stationary, right? So, all right, now, if I recall, now introduce L, which is the absolute value of the gradient of W, and I just recall the definition of Q, it gives me this equation. So Q is coupled with L. And now I recall the definition of L, I realize that's actually an AGB equation. And in fact, it's a very famous AGB equation, it's an eikonal equation. An eikonal equation is a very simple thing. It says, I'm gonna start in the middle of the complex, somewhere inside the outside of gamma, and I'm gonna find the shortest path to the set gamma, gamma 0, the initial one. But how I measure shortest is by integrating the Lagrangian L. So you're really trying to minimize the integral of L over all paths that start from a given point and reach the boundary. It appears in optics and various other parts of physics, also a very famous equation, also solved the best notion of solution is also viscosity solution. Okay, so now if I look at this, this is really a mean field game, right? So if, let's imagine that now I have, so this is a little strange, right? But it turns out that Q is an occupation measure. For occupation measure of these particles, you have exactly Fokker-Planck equation with 0 right-hand side. Right, so if I have all these particles now, trying to minimize the integral of L from the initial point along the trajectory to the boundary, and now I start with some initial distribution of these particles, then their occupation measure, density of the occupation measure will satisfy this equation. Because the flow, the optimal flow will be along this vector field, right? You'll be doing, so W becomes a value function. Of course, I should have said that. I never said it anyway, but if W is a value function of this game, then what you do is you just do gradient descent along W. That's another way to describe what happens. And you follow exactly this vector field, okay? And so now if the initial distribution of particles is fixed, this is really a mean field game because now your flow is coupled with the objective that you're trying to minimize through this coupling condition. All right? Okay, so I see no objections. Good. So, all right, so how do we make it all rigorous, right? So first let's define all of this, right? So what do we call an equilibrium? So we fix an initial distribution. So it's very unusual. So we're not going to ask about existence, uniqueness of mean field game. It's going to be different. We will instead characterize properties of a family of equilibrium. This family will be parameterized by initial distribution mu, which I do not fix here. It's anything, right? And so for any given mu, I define equilibrium as a pair Q and L, where Q is this minimizing measure. Essentially, it does exactly what I described. It minimizes this distance, but now, of course, we'll look at it in a weak sense, so we take expectation. Now, I also have a coupling condition which becomes this, all right? Because Q, remember, Q is the occupation measure, so this is just one way to express the occupation measure here. And that theta is the first time you reach the the boundary of the initial gamma. All right, and so finally, what is the arrival time function W that we're looking for? It's almost the value function of this game, but I do this sneaky little thing. I say, well, there's a special area where L has to be negative. Remember, I take positive part here. And so the negative, when L is negative, it must be equal, this must be 0 when L is negative. And so L must be either positive or -1 over gamma. And when it's -1 over gamma, I set my W to infinity. Why? Because in the cascade equation, this corresponds to the area which will never be reached by particles. Okay? And so by definition, W is 0 at the boundary. And it turns out, and this requires some work, I'm skipping it, but the initial data, that the initial velocity is this, is equivalent to the terminal distribution of the particles when they reach the boundary in equilibrium. Okay? So you're looking for all equilibria parameterized by mu now that satisfy this condition. The set is non-empty because you can always start your particles right at the initial boundary. So you have a non-empty set of equilibria. It's not clear that for every mu you will have a solution, you will have an equilibrium, but we don't really care. Okay, so now I'm going to define my super solutions. If you remember, I'm after defining a concept of a solution here. So I'm going to define it as this W, which is the arrival time function of some equilibrium. So a super solution will be exactly this W that I defined on the previous slide. But when I do that, I have to justify it somehow, right? I say, at least I should extend the classical notion of a solution, right? So here's the theorem that does that. I'm not going to prove it here. The proof is fairly straightforward. But you can show that for any equilibrium, its arrival time function does solve this PDE weakly, and this mu that appears on the right-hand side is exactly the initial distribution of your particles. So you can precisely connect all these equilibria to these solutions of this equation, through mu. Converse is also true, but you need a bit of smoothness, right? So if you have, in fact, a classical solution and your initial domain is smooth enough, then you cannot expect, usually you cannot expect to have a global solution, but if you have a local classical solution, then locally in this sublevel set, it corresponds to the arrival time function of some equilibrium. So you can go back and forth. Right, so we identified now super solutions with equilibria or arrival time functions of a family of mean-field games, and I'm going to use it now as a notion of a solution. Now we go to next step, which is now we have to extract a minimal element of this space of super solutions to call it a solution. And so the way I'm going to do it is the following. If you remember my one-dimensional example, the points where the PDE is violated and becomes inequality are the points where energy is lost. And you can just stop your interface for no reason and declare, I'm done, right? And that means you lose your energy too early. And so the idea is that you want to make sure that you don't lose, you lose as little energy as possible for as long as possible. But long is measured in this physical time, right, which is W itself. So in other words, you want to make sure that you lose as little mass as possible in any sublevel set of W of level T. And since we know that the loss of energy corresponds to the initial distribution of particles in the mean field equilibria, the condition becomes this, right? This is the lost energy in before physical time T. And you want to minimize that. So you want to have, so minimal equilibrium is the one such that you cannot find another one that loses less energy at earlier times. Okay? So it's a notion of minimality. It's a partial order on the space of this equilibria. And so we define a solution, we set it to be a minimal super solution in that sense. Okay? This is where one has to be a little bit creative and you can come up with different notions. And so this is a little bit sketchy, right? But that's the choice we made. So that completes step 2, right, in my program. So far we haven't done any mathematics. It was all just modeling and creating things. So the real mathematics starts actually in step 3. So step 3 is where we have to prove compactness, to prove existence of this minimal element. It's usually very easy. You define a functional that's monotone with respect to this partial order, and you just take epsilon optimal minimizers of this functional, and then you pass to the limit, right? But to pass to the limit, you have to have pre-compactness or compactness of your set. So the really interesting thing here is, Okay, so this is the notion of a solution, and then I'll go on to the third part. The really interesting thing here is to prove compactness of the set. So this is just a formal notion of a solution. What do we call? Of course, when you pass the limit, very often you get outside of your set, so you have to consider closure of all these equilibria, and hence the definition. So a solution, W is a solution to the cascade equation if there exists an approximating sequence of equilibria such that they satisfy the boundary data. They converge to a W for any capping T. By the way, remember, W can be unbounded because W is the time your domain reaches a particular point, and your domain may take a very, very long time to reach it. So in principle, it's unbounded. It may take value infinity at the points that are never reached by your domain. Now, it also has this minimality property, and this is exactly what I discussed heuristically in the previous slide. This is just really a more formal way of stating it. And again, here, one can be a bit creative and come up with other concepts. Hopefully, they will all lead to the same notion, but this we don't know yet. Okay, so third part. So how do we prove compactness? And this is really where geometric measure theory comes in. And these results now are indeed limited to d equal 2. There is one bottleneck in the proof that we cannot overcome. We cannot bypass it. Again, because of some deeper results from geometric measure theory that we use. That only hold for d equal 2. So let's assume that d equals 2, v0 is strictly positive, and gamma 0 is a finite perimeter set. So this normalizing constant kappa was introduced before. So here's the theorem. It turns out that for any equilibrium, you can put a bound on the perimeter of its sublevel set that is uniform in time and uniform over all equilibria, and only depends on these two constants, kappa and gamma. And that's really the main result of this work. Okay, so I'll show you the proof, but first the corollary. What comes out of this, of course, is that using that, you can basically control total variation of this function W minimum T, and that means you can get compactness in L1 local. And as a corollary of the corollary, you get existence of a solution. Okay, so really, the only thing that we need to prove is this theorem, which is really the main result, as I already announced. And so that will be the remainder of my talk. So, yeah. Sorry, can you speak up?
Is it a little bit sort of isoperimeter?
We don't, there's no isoperimeter. Perimeter is not preserved, right? It's not preserved and it's not decreasing. It may increase, right? So it's not like that. And it doesn't follow from any known isoperimetric inequalities. No, you have to prove it by hand, and it's not a preservation of perimeter. Yes?
Can you explain the intuition for, compactness aside, it's not obvious that there would be a minimal element in this partial order. Is there some intuition for why you would expect that? Is there like a lattice structure here?
You can easily define a functional, so I have to go back for that, right? You can easily define a functional for which is monotone with respect to this partial order, and it's continuous. It's just an integral. Just take an integral of this. You just take integral of this over times. It's monotone with respect to this partial order. Just take integral of this quantity. Okay, the right-hand side, the left-hand side doesn't matter. Take integral over little t from 0 to capital T. This functional is monotone. So if you have what is this? If you have one function that's less than the other one in this order, then the value of the function will also be less than the value, so it's monotone. And then you can show it's continuous as well with respect to, okay, so here you have to be careful, right? You have to be continuous with respect to the right topology, but it will be, at least with respect to W changing in the L1 local. And that's pretty general, I think, yeah. If you have notion of minimality, partial order, any monotone functional that's continuous, and you get compactness, you get existence. I mean, we prove it by hand. We're not relying on any kind of general results here, but I think it's a pretty standard result. Yeah. We're not claiming, by the way, there's no uniqueness here, right? Maybe that's confusing. It's a partial order, right? So minimal, it's not the minimal, it's a minimal. Yeah. So that's, maybe that was the question about that. But that's easy, yeah. So that's the really easy part. Okay, so back to the proof, right? So what we're proving now is this perimeter estimate, right? So let's see how this is done. So, okay, so we're gonna prove it by saturation. So we're gonna prove the following inequality, that at time theta, theta is the time when your particles reach the boundary, that in fact, my bad. So so remember, the condition for the boundary data was that this quantity, this distribution, is gamma plus something times Hausdorff measure, right? So this inequality is always satisfied when we define an equilibrium. And what I'm going to prove now is that this inequality implies the perimeter estimate, right? So just another way of stating the result. Okay, so how do we do this? So first, the perimeter of this set, of course, is the same as the perimeter of its complement. So the complement has the advantage of being an open set. Okay, so let's take this open set. It splits into countable union of, in principle, connected open sets, but I'm not going to look at connected components. I'm actually going to look specifically at these OIs, which end up being the interior of the level sets of this function. And you can prove that this is the case. Okay, so OI is the interior of the level set, not necessarily connected. Okay, so then what is sufficient is to prove this inequality. What is this inequality? It's a saturation. It says that the density, roughly speaking, with respect to Hausdorff measure of Y0 on the boundary of every OI is at least gamma over kappa. Why is it sufficient? Because of the lower semi-continuity of the perimeter. So the perimeter of O will be less than or equal than the lower limit of the perimeter of these finite unions. Every one of them is just this integral, right? And now if I integrate this inequality over this set, of course, probability measure integrates to 1. And so you immediately get a bound on this integral, which is kappa over gamma, right? So really what we want to prove is that somehow in every equilibrium, it must be the case that the initial locations of particles along the boundary of the set O somehow saturate the boundary. They have density that is sufficiently large. And that's enough now, because the mass of all particles is bounded, so perimeter must be bounded. Okay? Now, how is this done? So this is our new goal, right? Saturation. All right, so this is just a reminder that OI is the interior of the set. And before we prove the saturation, we're going to prove a slightly different version of saturation property, where I replace 0 by tau t. What is tau t? Tau t is the first time when the particle reaches a t level set of W. So it's like you do gradient descent of W over W and you reach level t. So how do we do that? And it turns out that this inequality follows exactly from the coupling condition of the game. So the game is designed in such a way that somehow it preserves perimeter by its structure. And how do we do this? This first line here is exactly the coupling condition with a test function chosen like this. I choose any nice function phi, and then indicator that W is between t minus epsilon t. So I'm looking at my particles between the two level sets of W, t minus epsilon and t. I plug it into my coupling condition, I get this equality. So this equality is just a given. It's a property of equilibrium. Now I notice that this red part is less than this, right? So I drop 1, I divide by gamma everywhere, and I realize that I recall that L is actually a gradient, absolute value of gradient of W. So even in the game, you can prove that this is actually the case, almost everywhere. So now I obtain this inequality, and here the integrating Y over this set is the same as looking at the paths of the particles between times tau of t and tau of t epsilon. So when you reach the level t, and then when you reach the level t minus epsilon. Okay, then I notice that the left-hand side, in fact, by the co-area formula can be written like this. And as a result, I obtain the inequality between this is less than this. On the next slide, I will start with this inequality that we just proved from the coupling condition of the game. Right, so we have shown this. Okay, this is what we've shown so far, and this is our goal. But look at this. What I have on the left, if I divide by epsilon, set to the epsilon to 0, I basically get integral of phi with respect to Hausdorff measure. Now this requires some justification, right? It's not so easy to pass the limits, but you can make it all rigorous, and indeed this is the case. And on the other hand, what I have on the right-hand side, again, if you forget about phi for a second, phi is nice and smooth, so think of it as a constant locally. So the integral of L itself, I'm integrating my L between the level set t and t minus epsilon. But my value function is exactly the integral of L, right? So it's exactly epsilon, right? Because my value function is an integral of L over the optimal path. So I get this epsilon here, I divide by epsilon, and I basically get this. And the left-hand side you can prove converges to exactly the integral of phi over the essential boundary of this sub-level set, W less than t. Okay, so we got this estimate, and recall this is what we need, right? We need this, but of course you can understand this by multiplying by test functions and integrating, which is almost what we got, right? So this right-hand side is almost what we want here, but integrated, right, with respect to test function phi. And now we just need to, well, we need to extend this set a little bit, right? We don't care about this set, we care about OI. But you can show that the essential boundary of OI is contained in the union of these two, and you can repeat the same argument to obtain analogous inequality for this set. And so therefore, you get saturation on the union of these two, and therefore you get saturation on the OI, the boundary, essential boundary of OI. Okay, so you got basically what you wanted. And now, yes, yeah, I'm almost there. It's nice because you don't see how many slides are remaining. It's good. So we have proved the saturation property, but unfortunately with tau as opposed to 0, right? I need it at 0, and it's important, and I only got it at time tau. So I need to somehow prove that tau in fact is 0. And this is where the bottleneck is, and this is where we have to assume that d is equal to 2. So we prove the following lemma, which follows from some general result by Ambrosio on characterization of essential boundaries of open sets of finite perimeter, no, in general, finite perimeter sets, but in dimension 2, okay? And using that characterization, we can prove the following property. Now, in fact, what we prove is slightly stronger, but for simplicity in this presentation, I kind of simplify this result. Here's what it says. If you have two disjoint open sets, their boundaries may intersect, of course, right? And the intersection point will be on both boundaries, topological boundaries. But it doesn't, in general, have to be on the essential boundary. But it turns out that if they are indeed open connected, then almost every such intersection point must be also on the essential boundary of each set. That's what this lemma says. And it seems like it should be true in dimension above 2, but we cannot prove it, and we don't know if it exists. Asked around. Nobody in analysis seems to know. But we proved this result for dimension 2. So this is, again, I skipped the proof. It's interesting, but we don't have time for that. And so now I claim that this is enough. It's enough. This result is enough to show that tau must be 0 by contradiction. And my proof is, and that's the last slide, is by picture. So let's assume that tau is not 0, and I'm going to find a contradiction with that lemma I just showed you. Okay, so here's the picture. This is our OI. It's inside this level set. Typically, you can think of them coinciding. So this blue stuff coincides with the black one. This is your point y tau. Let's assume that tau is not 0. That means the path of y came from somewhere else. But if it came from somewhere else, it must have come from a super level set of W. And it must continue also to the sub-level set of W. So it came from this W above T and moved into this W below T. Now, it's not obvious, but you can, in fact, deduce, well, let's assume also these are these open sets. They're open sets. Let's assume they're connected, okay? Now, in practice, they are not, and that's why that lemma I showed you has to be extended, and we prove a stronger version of this. But for simplicity, let's just assume they're connected. Then you have three sets intersecting at this point. If you have three sets intersecting at some point, then they're disjoint, but their boundaries intersect at some point. It's clear that the normal cannot, at least one of them cannot be defined at this point. Just think about it, right? Three sets, one of them must have a sharp corner. And you can make this rigorous. And so the thing about the essential boundary of a set is that you know that at almost every point on the essential boundary of a set, you should have a normal, well-defined normal in measure-theoretic sense. And this is simply impossible in this picture. At least one of these sets cannot have a normal. So, because we know from previous lemma that this point must be on the essential boundary of all these three sets, you get a contradiction with the existence of a normal. And that's it. That means tau is 0, and we complete our proof, and I'm done. Thank you.